4.7 implicit differentiation. We're going to go through a couple examples here of a process we need to use when we have a function that isn't defined explicitly, and we'll explain that in a minute. But before we begin, you'll see the first page on your notes has 3 warm-up problems, right? So I want you to take your time, play with those. You can even kind of work with each other a little bit after you're done, or even while you're doing them. Pause the video if you need to. In a couple seconds, I'll get you the answers to those 3 warm-up problems. And when we get together as a class, we can go over whichever ones you're still not sure of. All right, so the first warm-up, the derivative was 3 ln of 4x plus 3x minus 2 all over x. That's about as simplified as you can get. Second problem was e to the square root of x plus 6x, that's how it started, times 1/2 x to the negative 1/2 plus 6. Third problem is probably the most challenging. Just so you know the derivative, you'll need that for your slope. The derivative was 4 times 1/2 quantity 3x to the negative 1/2 power times 3. So that was a chain rule. And then the actual equation of the tangent line, which is what they asked you for in that problem, was y minus 12 root 2 equals the slope, which wound up being some ugly number, 6 over radical 18, times x minus 6. Again, we can go over any one of those if you want. All right, so now taking kind of a turn into the process of this implicitly defined function thing, let's talk about, first off, what is the difference? Why would I need to use a different process here versus, what we've been doing, right? So these are examples of things that you have been taking the derivative of. E to the 4x, y equals, 5x squared plus 8. Here's one we did recently, right? 2x to the 4th plus 1 all to the 10th power, stuff like that, right? But here's the big difference. You'll notice that in every one of these cases, you keep seeing y equals, right? So that's what we call an explicitly defined function. Like there's no debating what y is equal to. An implicit defined function, that's different. So that might be where you have a blend of x's and y's in the problem. You could have like x squared y equals 6. Or, 3x plus y to the 3rd equals x or something like that. Where maybe we could solve for y, but it might not be the most convenient thing to do. So we have a way to deal with that, and we're going to walk you through that process. So the first example is 3x plus 4y minus 5 equals 0, right? And so the first question you would have to ask yourself is, how do I know that I'm supposed to even do this? And the bottom line is, if the problem doesn't say y equals, this is probably your best bet. You're probably going to use this process. So I'm just going to get a little creative here. I'm going to rewrite this for a minute. 3x plus 4, and then watch this. Instead of writing y, how about if I write y as f of x? Okay, you don't necessarily have to do this, but I'm just kind of showing you a point here, and you're going to figure out why we're doing what we're doing. So let's suppose now we started to do the derivative, right? So we're going to take the derivative of each piece. So the derivative of 3x is 3. Now here's where things get a little bit interesting, right? The derivative of 4 times the function is 4, because it's a constant, right? Times the derivative of the function. So how do we write that? Well, it's just f prime of x. And then as we know, the derivative of 5 is just 0. Same thing over here. The derivative of 0 is just 0. So step 1, right, will be to derive everything, right, on both sides. So that includes the right side as well. And then step 2 is to solve for dy dx, because that's your derivative. Now here's our issue. The way I did it, you don't even see a dy dx, so let's kind of understand that it's there, it's just not easy to see. So 3 plus 4, and then how about this? Instead of me writing f prime, one of the things we learned was that you have multiple ways of saying the same thing. So f prime of x is the same thing as dy dx, right? So now it becomes a little clearer what we're supposed to be doing. If I'm supposed to be solving for dy dx, then I need to algebraically move some things out of the way. So I need to take 3 away from both sides, right? And I have 4 times dy dx equals negative 3. And so dy dx equals negative 3/4. Okay? So that's the idea. Now you look at that and you say, well, it doesn't seem too different. It's not that much different, but it gets a little bit more involved depending on how hard the problem is. So we're going to look at the next example so you can kind of see how this works, because there's a little bit of nuance there to the next one. So the next example is 3x squared plus 4y squared equals 2x. So remember, our steps were, first and foremost, you derive every single thing, right, that you see. So this derivative would be 6x. And then here's the tricky thing, right? This derivative would be 8y times dy dx. Now, why is that, right? Let's get to that in a minute. This derivative would just be 2. So let me come over here for a second. This is probably the last time I'll show you why this has to be, but if we take that approach that 4y squared is really 4f of x squared, then you have the chain rule going on here, right? So you have 4 times 2 f of x to the first times the derivative of f of x, which is f prime, right? Well, if you look real carefully at this, this is basically 8y, right? Because remember, f of x and y are the same thing. And then f prime is dy dx. So here's a little note to take with you, okay? Every time you derive something that has a y, you must put a dy dx after it. So let's write that down, right? Every time we derive a y term, you must multiply by dy dx. So this will avoid you having to sit there and kind of like show this proof that I'm showing on the side here. So that's where I got 8y dy dx. So now if I can just do all that, then my solution becomes easier, because all I'm trying to do now is solve for dy dx. So dy dx has to be 2 minus 6x all over 8y. Okay, again, that's not going to be enough for you to feel good yet, so let's do another example. Let's take a look at example 3. All right, so example 3 starts off as x squared plus y squared equals e to the x plus e to the y. So remember what we said on the previous slide. Every time you derive a y term, you have to add a dy dx. So we'll derive every single one of these 4 things, right? The derivative of x squared is 2x. Here's a y term, right? So the derivative of y squared is 2y, but what did we just learn? We have to put in a dy dx here. Okay, equals the derivative of e to the x, so that's just itself. The derivative of e to the y, well, that's just itself, but, right, it's a y term, so we have to add in a dy dx. So let's do that. Okay, once you're here, the calculus is over. And now we have to solve for dy dx, right? So in this case, we have multiple dy dx's. They're not on the same side of the equation, so we want to get them together. Doesn't really matter how you do it. I'm just going to move this one over to the left. And while I do that, I might as well move things that don't have a dy dx over to the other side. So what that would look like for me would be 2y dy dx minus e to the y dy dx, and that would equal e to the x minus 2x, right? How do I solve for y here? Well, you notice I technically have a GCF, right? Both of these terms have a dy dx, so I'm going to take it out, right? And that would leave me with 2y minus e to the y. And so my final answer, right, I'm just going to divide by all that so that it crosses out. And I get e to the x minus 2x over 2y minus e to the y. So I understand that it's confusing. This is not an easy thing to learn via video. So obviously we have to kind of go through this together, but we're just trying to make sure you kind of see just different examples of the process of implicit differentiation and things we have to remember. So let's just kind of recap, right? Let's break it down to a 3-step process, why don't we? Okay. First step, right? Derive everything. Derive every term. And you want to make a note here, right? All the y terms, right? You got to put a dy dx. Okay, so second step, right? Let's say all dy dx is to one side, right? And then finally, solve for dy dx. And I'm just thinking out loud right now, like maybe we go back to that first note, and when we say derive every term, we should remember we said it on one of the other slides, on both sides, so not just on the left side, for instance. Okay. Let's look at one more example. And again, we'll have to, anything we have to clean up in class, not a big deal, but we just want to get you introduced to the process. Just got to keep practicing, really, is what we have to do. And we'll do that next class. Final example, example 4, says find the line tangent to x cubed plus xy plus y cubed equals 5. And all that's taking place at -1, 2. So let's get into the derivative here. Remember, my answer is going to be y minus 2 equals some slope, which I can't find until I derive it, times x plus 1. So I already know this is my answer. I just got to find that box right there. So let's derive, right? X cubed becomes 3x squared. Xy, guess what? That's going to involve some product rule. So x times the derivative of y, so x times dy dx, right? Plus y times the derivative of x. Boom. So remember, when I took the derivative of the y term, that's what got me the dy dx. Plus derivative of y cubed, 3y squared, but it's a y. Another dy dx there. Derivative of 5, 0. So if you have to pause this video, I didn't mention this before, but if you have to pause this video, replay it, stop term by term, that's okay, because this is a very new experience and a new problem here for you. So you want to be able to backtrack to how we got every one of these terms here. Okay, step 2, get all the dy dx's on one side, get everything else out, right? So right now I have x dy dx plus 3y squared dy dx, right? That will equal, let's see, negative 3x squared looks like minus y. Factor dy dx out. And if I'm going a little too fast, pause, kind of do your thing to catch up. But here's my final derivative, right? Negative 3x squared minus y over x plus 3y squared. You can't really cancel anything out here, so you just kind of have to leave it. Now remember, this is the missing piece we need, right, to get me up here to my slope. So what I'll have to do now is I have to plug in the point they gave me, right? X is -1, 2 is y, to get my actual slope. So -3 times -1 squared minus 2 over -1 plus 3 times 2 squared. So let's see what that gives me when I do the math here. -5 on top, and -1 plus 12, so 11 on the bottom. So it looks like -5 over 11 is my slope. Okay, so again, it's a little bit of a longer video, but try to do some of the problems that follow. Try, the next 4 on the last page there. Let's see, we're going to have some questions. Let's see what they are. Kind of make note of where you're getting yourself lost if you get lost. And remember, you can always watch this video again.